So, filters. What are the filters what we are talking about here? Some fundamental definitions like how to characterize filters. So they are, in general, filters are divided in few classes by their spectral response. The first one, probably the most common, is low-pass filter, which means that lower frequencies pass through the filter virtually unchanged, while the higher frequencies are attenuated. High-pass filter is the opposite of that one, so higher frequencies pass through the filter. Band pass, okay, you guess that one, okay, band. There is a band or certain range of frequencies which are passing through. Band stop means that you will attenuate certain frequency, and then we have these multi-band filters, which are practical. It's just the combination of previous filters. This is actually something you will be probably playing more next fall. You have the digital signal processing, I think, coming on the on your next fall classes. So basically, if you have a low-pass filter, it's characterized by the following parameters: the passband. That's the where this signal goes through without any attenuation. By the way, oops, magnitude. This should so magnitude, not magnitude. So there is a typo. It has been there for at least 10 years. Sorry about that. Yeah, there was a question. Are you recording? Yes, I am recording. So recording also all my mistakes here. Okay, but anyways, so the magnitude scale or the vertical scale is for filters, it's usually logarithmic scale, meaning in decibels. Decibel is the unit for signal power. So basically this would show the signal power distribution over the frequencies. For analog signals, also the frequency supposed to be in logarithmic scale, but I just cut some corners and used a filter from my digital signal processing course. Okay, so we have a passband, which basically ends somewhere around there with this corner frequency, FC, corner frequency or cutoff frequency, either or the same thing. Sometimes it's also referred as -3 dB frequency. But anyways, it's still the same. It defines what is your passband. So what is the band where the signal passes through the system without any attenuation. Stop band, the green one here, that's the band where signal gets attenuation at certain level. Okay. Then there's that blue region, which is transition band. In analog filters, sometimes this is actually just omitted, and basically the stop band is considered that it starts immediately when the passband ends, so the corner frequency are the same. On digital filters, the passband the corner frequency. Passband is different from the stop band start frequency. And the transition band actually means how steep the filter is. So how much you actually need to change the frequency from passband signal to stop band. But anyways, so in here, no attenuation to the signal. In here, stop band, for example, at that level, that will be minus 20 decibels. Minus 20 decibels is 1% of the power of the signal. It's left. Okay, so that's for the low pass filter. Most importantly, corner frequency. Yep. And yes, that's basically what I'm saying. This is for analog signal, analog filter, corner frequency somewhere in there. That will be about that minus 3 dB point. I just eyeballed in, I think it's more like minus 4 dB here. But anyways, we have a pass band and we have a stop band. So interestingly, actually, what this one is, it's the same as how this RC circuit here works. So calculating the U out divided by U in gives this so-called amplitude response picture. So we have a pass band, stop band, and we have a cutoff frequency. And a couple of details here. This is almost virtually no attenuation here, small frequencies. Oops. And then we have the stop band. After that corner frequency, the attenuation starts increasing roughly at constant rate of minus 20 dB per decade. So when your signal frequency changes 1 decade, which is from 100 to 1000, for example, this attenuation drop is about 20 decibels. Same, for example, from 500 to 5000. This attenuation drop here is about 20 decibels. So that's actually for the first degree filter. Okay, more about those maybe later on. But anyways, corner frequency again. That's where the basically defines the filter property. High pass filter parameters, same, but the opposite. So higher frequencies are passing and lower frequencies are stopped. And the transition bandwidth is in between. Corner frequency is still defining this pass band. Okay, low pass versus high pass filter. This is a small simulation I made on Octave program. Very simple one. Let's consider first that we have the original signal is the highest picture here, which has a low frequency signal. And in addition to it, it has some sinusoid signal, so it might be this could be, for example, a sensor which gets a hit, and there's also some ringing into it. Maybe a piezo element put into a metallic plate. When you hit it, you get that big warping of the metal plate, but in addition to that, there's that sound wave that gives that smaller the higher frequency component on it. Okay, so for low pass filter takes out this higher frequency component, and then you get this low pass filtered signal. So if you would be using low pass filter if the higher frequency signals are considered to be the disturbing part. For example, in reduction of interference, meaning, okay, if that was a very sensitive circuit close to open AC wires, it could be picking up some AC humming noise, so line humming, or switch power supplies are actually giving that electromagnetic interference. And if you have switch power supply next to a very sensitive sensor, you might actually get some sort of periodic signal showing up on the top of this the top of the original signal. So that there you would do some reduction of noise. Or if you have a higher spectral random noise there, you can try to reduce that noise by filtering with a low pass filter. On the other hand, it could be the opposite way. If you are interested about those higher frequency components, and that basically this lower frequencies drifting of a sensor, this bias level, for example, then you would do high pass filtering to see just that the higher frequency component there. Okay, for example, well, a couple of examples. Radio receiver. Okay, radio receivers actually have these kind of high pass filters for taking out the DC part. Another one, quite a nice example, I think I have a picture later on, is DC biased microphone signal processing. So have you ever thought of how these old-fashioned headsets actually are working? How to provide, oops, just a moment, I need to change the channel here. Okay, just the, oops, let's not advertise. This is analog system that can be plugged into any of the sound connections, 3.5 millimeter jack. Have you ever thought of how they actually work? You have different kind of signals on single analog line. You also have these push buttons. In this case, I have only one, but in some cases there might be even four. In this, you have a signal only for the microphone, and then two of those rings are for these loudspeaker left and right, and then ground. But still you have the microphone signal and this information about the buttons. So there must be some smart way of checking if the button is pressed or not. Okay, so, well, low pass, high pass, this is pretty straightforward. Low pass filter passes the lower frequencies and high pass passes the higher frequencies. And that I have the headset specifications right here. So yes, that is actually exactly the same as my headset picture, the 3.5 millimeter jack there, and that's how it's connected. The tip is connected to left loudspeaker, and then the right is connected directly to the right speaker, there's a ground. So oops, what happened? Ha ha ha. Sorry about that. I pressed something. There. So the right, this second ring here actually is for the ground, common ground connection, and then the sleeve ring here. Sleeve actually the leftmost in this picture, that is connected to the microphone. The microphone usually is type of electric or electret, which basically this symbol shows what it is. It's practically two very thin membranes which are made of conductive material, or actually the other one is solid and the other one is membrane at the top of the solid, the conductor. So in principle, it's a capacitor. When you bias that one, put a DC voltage across the capacitor, then the air pressure is actually vibrating that membrane up and down. So it goes closer and farther away from that the other terminal, and that produces very small current. Okay, but for that one to work, you need to have a bias filter, a bias circuit. So on your computer or your mobile phone end, there is a, well, Thevenin's model. There's a bias at 2.2 volts with a resistor. So known 2.2 kilo ohm resistor. So practically this powers up that microphone, electric microphone, so that you have this signal analysis of UHS. That actually has the amplifier to amplify that AC circuit, AC signal coming from the microphone. Okay, so the power supply for that microphone is actually from that very simple 2.2 volt and 2.2 kilo ohm Thevenin's model. And this is actually directly from the specifications. Okay, so that's the microphone signal. Then there was these buttons, up to 4 buttons on this on the specification. The simplest and the difference between those buttons are actually they have different resistances. So for different purpose. So one of those switches, I have only one, that's the mute switch. So when you press it, basically it just shorts that signal wire, meaning that then you can detect, okay, 0 volts. 0 volts at input, meaning, okay, now we have a mute button is pressed. Compared to this microphone signal is around, say, maybe 100 hertz to a couple of kilohertz is the voice, human voice frequency range, around that one. So 200 to 2 kilohertz or something like that. So basically that's high pass filters for the signal analysis. But these events, this button press events, they happen once in a while, very low frequency. So practically that's the low pass filtered in one sense to check which button is pressed. Okay, so yeah, so the other 3 buttons, when one is mute, then I think it was the volume up and volume down, and then third one is something. No, I don't. Okay, that might be this the cancel call or the yes, cancel call. Yes, that must be it. So there we have the buttons and microphone signal on one single analog signal line, and the signal analysis actually takes care at that all of those signals are filtered properly and the functions are done accordingly. So simple headset specification example on the filtering. Let's take it back to the say engineering. Any signal processing circuit actually can be represented by that kind of formula. So output as a function of omega, or actually it could be function output function at the function of time. Okay, sorry, this could be actually of time. But anyways, its alternating signal output is the same as the frequency response times the input signal. So basically the frequency response, you already saw a couple of those. So this is a frequency response, one half of it. So basically this is the amplitude response graph showing how the any signal is filtered when it goes through the system. Okay, it's a complex function, but again, nothing complex about complex numbers, plain old engineering. So it's a frequency response. H of omega is frequency response, and this can be divided into two parts. Well, it's a complex number. So for complex number, there's the amplitude response, which is absolute value of the frequency response, and then phase response. So that's basically the complex angle of the frequency response. The phase response will tell you what is the phase difference between the signal which is coming in compared to signal coming out, or actually the other way around. So it tells about how much phase is changing on that circuit. Okay, for sinusoidal signal. So this actually is for sinusoidal signals, periodic signals. With, well, here I have a zero initial phase and amplitude A, and I used cosine just because, well, it looks nicer on this picture. So there I have the output. This a little bit bothers me actually, that this output actually is a function of time. If the sinusoid is A times cosine of omega t, then of course the output is also function of time and also the frequency. But anyways, it's simply you just multiply that input sinusoid signal with that frequency response, complex number. And you can divide it actually just like that. So we have the amplitude changes that much. So the original amplitude times the amplitude response at that frequency. In this lower picture, we had this signal amplitude 1, and after the filter it dropped to 0.45 or something like that. So that's the change in amplitude. And then that phase response is simply a phase shift inside of the sinusoid. And basically in here I have the phase shift from these to there. It's a little bit hard to tell, but I would say about 30 degrees or so. On the other hand, it would be easier to, from this kind of graph, say, okay, it's so and so milliseconds. So phase shift on sinusoidal signals, it also always marks the what is the actual time shift, how much the signal is delayed on the system in time. But for mathematics point of view, it's much easier and simpler and better to use the phase response. So on mathematics, and we have this amplitude response is the then that absolute value. Okay, so that happens for any sinusoidal signal. What happens to different kind of signals? If you are considering random signals, then you could actually think of, okay, or any random signal also could be represented as Fourier transformation. So sum of different sinusoids. Okay, so practically this works also there. How about this kind of if you have a digital signal, meaning a state changes from 0 to 1. That's when the things get a little bit ugly. It's called transient. And the transient analysis, I don't think that we will have time for the transient analysis on this course. Anyways, there are some tools that you can do transient analysis when you just believe that it still follows practically the same formula. Then you don't anymore talk about frequency response. Basically the same thing with the general term would be the transfer function of the system, but it's just one extension more. Here we are concentrating only on periodic signals because that's basically what fundamentally these filter. They are based on different frequencies, selecting different frequencies. Okay. Back to this example, RC circuit. So we have the output is the same as input divided by 1 plus j omega RC. That was already, well, this comes from the voltage divider equation. We already show that one. And basically the output is directly proportional to the input signal. That's good. But it also depends on the signal frequency by this part, which is basically 1 divided by 1 plus j omega RC is the frequency response of this system. Okay, so looking at this formula, actually, and especially that omega, if you have DC, meaning that frequency is 0, actually then omega is 0 and this basically output is the same as input. So the divider part is just 1. On the other end of the frequency range, if a frequency is very high, so omega is gazillion, much bigger than this 1 over RC. So basically, omega RC is around 1000. Then basically we don't have much of anything left from the signal. So it becomes this complex number, but anyways, think of that it has the magnitude and the phase. Phase is this part, but the magnitude here is actually 1 divided 1 let's see, square root of 1 plus omega square r square c square. So that magnitude part goes to very small. So okay, lower frequencies pass through the signal virtually unchanged, and the higher frequencies are attenuated. It sounds like the low pass filter. And here I have even some nice Tinkercad simulation for it, just to show. Okay, let me expand it a little bit. Right, there. So I have a function generator, and then I have resistor and capacitor. The resistor value is 1 kilo ohm, and the capacitor value is 100 nano ohms. Then I have the function generator here, starting frequency at 100 Hertz. And a couple of oscilloscope. The left oscilloscope is measuring the input signal for the circuit. So that's directly what the function generator is giving. And the other one is measuring the voltage across the capacitor. So practically it is measuring exactly that, nothing more. U in from function generator, and which is also measured by the first oscilloscope, and then the second oscilloscope is measuring the output. Let's see if the simulation works. Yeah. So at 100 Hertz, we have roughly the same signals here on input and output. Let's change this a bit. So at 300, still the same. Okay, now something changed around 800 Hertz. The input amplitude is still the same. So input amplitude, peak to peak amplitude actually is 1 volt. So, wait a minute. 1 volt. Yeah, yes, it's 1 volt. Peak to peak. But now it has attenuated. So on the rightmost function generator, you can actually, the whole range is 1 volt. So this is already less. So it's about 0.9. Higher frequency again, and now we have the peak to peak is something like 0.5. Okay, even less. Unfortunately, those oscilloscopes have a different scaling. This auto scaling. Whoops. Something went wrong on the simulation. Okay, that means that the leftmost oscilloscope does not anymore work quite well. But anyways, so it's a low pass filter. Let's see if I can actually change this one like that. Lower frequencies. Lower frequencies to higher frequencies. Yeah, there. So higher frequencies are cut off. So yes, we have a low pass filter. So the previous, actually, on the RC low pass filter, the mathematics goes something like this, so that the frequency response, that's always the U out divided by U in, and in this case is 1 divided by 1 plus j omega RC. The real part of that one is 1 divided by square root of omega square r square c square. Well, that's how you take the absolute value of the complex number. Nothing fancy here. Then the phase response is the complex angle of that one. And doing the math, I just cut corners usually, just like in here. Doing the math here actually shows that the complex angle is same as minus arcus tangent of omega RC. Okay. So the amplitude response and phase response, just like that. And here we have the an example frequency response of RC low pass filter with those component values. R equals 2 kilo ohms and C equals 1 microfarad. Then we have the cut-off frequency. It's around here, so it's about 80 hertz or so. So that's the cutoff frequency. Basically, if you want to know the what is the cutoff frequency or corner frequency, then you just calculate f c equals to 2 pi r times c. Let's see, do I have a calculator there? 2 times 3.14 times r was 2000 times c is 0.001. Something went wrong. I got the wrong number here, but anyways, from the graph, it's around there. If you want to play with these responses yourself, actually, clicking this picture will open a Excel, oh, not Excel, Google Sheet that you can copy to yourself, and then basically, okay, still working. Haha, everyone else is also working. There we have those pictures, and if you change this, for example, to 4000, then it changes the frequency response accordingly. You get lower, and then let's see, 1000. Wait a minute. Do I have a mistake here? Maybe. But anyways, so you can play with this. Ah, there we have, with the corner frequency. So yeah, so making the R times C higher will change the corner frequency lower. Remember this one. So practically the R and C are used to tune the cutoff frequency where you want it. Anyways, have fun playing. For low pass filter, RC low pass filter, there's a very simple formula to calculate this corner frequency, which is also the same as minus 3 dB frequencies, 1 divided by 2 pi RC. Yeah, and attenuation at that frequency is half of the original signal power. And the phase shift of the signal actually is 45 degrees. Okay, let's take a little bit back. How come half of the power? If you do the math here, you get that amplitude response value is the same as 1 divided by square root of 2. Okay, magic. Okay, so anyhow, this is how the physics and engineering work. And the corner frequency, or basically minus 3 dB, it's not just a randomly selected. Okay, let's decide that. Okay, minus 3 dB sounds like a good place to put this corner frequency value, since it fits the numbers. No, it actually selected the other way around. It's selected so that the half of the signal power is left there. Okay, which happens at the phase shift of signal 45 degrees in this case. Good. Then reversing those components on R and C. Well, actually, now we have the same system, and this is quite simple to think that, okay, if the low pass filter, the signal actually is across here, and there's this slows down the voltage changes. So capacitor is charging and discharging, taking out the current. So the most of the voltage change will happen here for higher signals. And okay, so this one eats out the high frequency component. The higher frequency component is charging and discharging this the capacitor. Okay, and if we have here signal actually a low pass filter signal, lower frequency components are unchanged, then the rest of this signal is across the resistor. Remember that Kirchhoff's rules are still working here, so that the total voltage U in is divided between the resistor and the capacitor. So if the capacitor signal of the amplitude response looks like that, then it must be that the rest of the signal is across resistor, which means that if you just swap the resistor and capacitor places here, you get this output signal now across the resistor, so referred to analog ground. So practically, this one works as a RC low pass, the high pass filter. Doing the math actually will prove it, but anyways, this is also quite, say, common sense. So here we have the amplitude response of the same circuit except swapping the C and R. And okay, corner frequency is exactly the same for high pass and low pass filters. So not much to change in the design. Just swap the RNC. Okay. We had also that inductance part. Now we have actually checked that, okay, having the resistor and capacitor, you can have high and low pass filter for small signals. Great. However, the electric power is consumed only on the resistor. There is no electric power consumption in inductor or the capacitor. That is a fact. The capacitor, it's just charging and discharging. There is nothing that consumes the power. The resistor, it heats up. So if there is a current flowing through the resistor, then it has the voltage change at the same phase, and when you multiply that current and the voltage, you can find that, okay, this part actually consumes energy, but the capacitor does not. That's because it just charges and discharges. And basically that voltage or the current and voltage, they have that 90-degree the phase shift. It also means that when you multiply current and voltage, if one is sine, the other one is cosine. When you integrate it over time for average power, it ends up 0. Okay, but okay, yeah, so only the resistor is consuming electric power. By the way, same thing for the inductor. It does not consume any power, ideally. So, okay, these ideal components. Of course, the real components, it's hard to make a capacitor which does not have some resistance inside, internal resistance, but that's basically a fault, not fault, but a feature of a real component. But here, when we are talking about these components, we consider these ideal. So, okay, electric power consumed only on the resistor. Only the resistors heat up. If a capacitor heats up, it's broken. If an inductor heats up, it's broken. Okay, so actually on the power consumption point of view, the capacitor blocks always low frequency current. So thinking of this, okay, one way I think of it, this blocks lower frequency current to pass through the resistor. Okay, so the lower frequency power is not getting consumed on that circuit. Low pass filter. Actually, this capacitor blocks the current flow of low frequency currents here. And again, that those currents don't pass through the resistor if this is open circuit here. So on the power consumption point of view, this functions always as the high pass filter for the current, the RC filter. Okay, when it's used on series. In power electronics, so if you want to actually have some lower frequency currents through a resistor and still have either low pass or high pass filter, then you can use RL circuit as a low pass filter. Actually, in power electronics, the RL circuits are used a lot. For example, the switch power supplies, they are in one sense, they are, well, yeah, they are power electronics. And in bigger switch power supplies, they still take quite a lot of space because they have big inductors, meaning they must have thick wire on the coils that it withstands the currents that are flowing through that coil. It takes some space. Okay. But anyways, RL circuits, they're used in power electronics. Another place where the RL circuits are used is in radio frequency filters. In radio frequency, capacitors have limited performance due to leakage currents and such, and there you cannot use the active filters, and basically they're in RF technology you use RL filters or RLC filters. And another reason, of course, is that in receiver side especially, you don't want to waste any energy, so the only option is to use the RL circuits. But for small signals, for small signal processing, you don't necessarily use any inductors at all. For example, small signal amplifiers, the audio preamplifier kind of things. Okay, but anyways, they look quite the same as RC filters. R and L in series. And if you take a look at this here, so our U out is U in times 1 divided by 1 plus J omega L divided by R. The difference between this and the low pass, the RC filter, is that downstairs, instead of C times R, we have L divided by R. But functionally, it's still the same. So you still can tune the filter cutoff frequency by a couple of components, so L and R. And the corner frequency for RL low pass filter is 2 pi R divided by L. I think it's like that. Is it like that? Maybe. Let's see, 1 divided by 2 pi R. Yeah, it must be like this. Yes. I started doubt myself. Ah, I'm doubting myself again. So practically it means that omega equals omega LR equals 1. Now I need to, okay. So how to calculate the 3 dB per point here is, would you check when that the h of omega is actually in here 1 plus j. That actually would be the 3 dBp point in which omega, which means that omega L divided by R equals 1, which means that omega is R divided by L, 2 pi F equals R divided by L. Hey, wait a minute, I have 2 pi on the wrong place. R divided by 2 pi L. Right. Yeah, I have a small mistake on my formula there. It happened, actually it affects on the exercise. I will make a correction to that one as soon as I can. Meanwhile, we just go with that. No wonder it looked funny yesterday when I and you actually went through this material. Okay, high pass filter, similar, but you just switch the L and R. Okay, math is still the same, cutoff frequency, corner frequency, okay, which is still wrong here. Sorry about that. But anyways, so that's all there is for first degree the RC and RL filters. Okay, and there we go. Example, two-way crossover filter. The basic principle of a two-way loudspeaker crossover filter is the following. First of all, the audio amplifier output. Oops, sorry, I had the wrong. Yeah, let's go back. So, yep, so RC low pass, and there we have the low pass filter. And for the high pass filter, you just change the R and L. And you have the quite familiar mathematics also here. In yeah, something like that. Okay, and then the example. Two-way crossover filter. So the principle looks like that. So we have the tweeter, which is the higher frequency loudspeaker, and then we have this lower frequency loudspeaker, which is called woofer. And then in some cases you have the third one. There might be 4 different channels, but anyways, it depends totally on how much you put money to your stereo equipment and loudspeakers. Why we are doing this one is to separate the inside of the loudspeaker box, the signal which goes to the higher frequency speaker and which signal goes to lower frequency signal the speaker. And now the signal is coming in basically a pair wire. So there's a ground reference and the signal. Okay, so this signal has all the spectrum when it gets out of the amplifier itself. So you need to do the separation inside of this loudspeaker box. And these physical limitations, actually, when you are making a loudspeaker for lower frequency, that requires big movement of air on quite large area. So it does not happen actually on smaller loudspeaker. It's very hard to get good bass from small loudspeakers because of physical limitations. Big movements in large area. Okay, which means lots of mass compared to highest frequency. Then you basically don't have that big air movements, but higher frequency means you get the same pressure, air pressure, with a higher, either higher speed or bigger dimension. And higher frequencies, that's basically the first one, which means that you need to have smaller scale, smaller dimension structures. Okay, so to cover the full audio range from 20 Hz to 20 kilohertz, you need at least 2 speakers. Usually they are, say, you're starting to say hi-fi when you have 4 speakers. Sorry, 3 speakers. So 1 speaker is good for just about 1 decade of frequencies. Okay, yep, that was some the trivia information. Okay, however, this signal is this is power signal, so you need to basically run these speakers, which are now actually shown as resistors, since in practice they are consuming power. So the model for the loudspeaker is a resistor. It's not inductor, also, although it's inductance which is driving that inductive coupling to magnetic field, which drives that the membrane there. But anyways, for the electronic signal point of view, it looks like a resistor since it consumes power. Okay, so anyways, there you have the capacitor and inductor, the higher part, C1, R1. That's for the current. That's the high pass filter. So higher frequencies are consumed in R2. Okay, but C1 also blocks the lower frequency currents. So practically then we have the lower frequency woofer down that R1, and it has the inductor L1 that actually passes through the lower frequency current but blocks higher frequencies. So this basically means that there's a high pass filter for this R2 and low pass filter for the R1. And now we are happy. We have higher frequency power is directed to the higher frequency tweeter, and then the lower frequency current is directed to lower frequency the woofer. Okay, and this is what they actually look like. It took for a while for Juho to find a Creative Commons license place to take a picture, since neither me or Juho had our own stereo speaker to break up or break down. This is a three-way crossover filter for loudspeaker. On the left, we have input for the loudspeaker. Lines are coming there. Couple wires, thick ones. And then we have three different bands. So bass for the tweeter, treble, oh sorry, bass is for the woofer, treble for the tweeter, and then we have even the middle for the, it also has its own funny name, but anyways, it's the middle, the frequency range. Okay, and only 4 components. Well, this, if you go and check that YouTube the video, you can see that this is a product advertisement on YouTube. This is very cheap. The crossover filter. So a three-way crossover filter, which means that one of those inductors is used for this one. So for the woofer, which is actually, it's right here. So this single inductor gives the low pass filtering properties for that external the bass loudspeaker. Then we have one capacitor actually is used for the high frequency component, which I would guess this is that one, because it's close to this treble channel. So the signal comes and it will be as just put there. And then we have both inductor and capacitor, 2 components left. So we have these 2 components, one inductor, one capacitor, that are for the median the speaker, median tweeter. I think that's called also tweeter. So practically those are connected in series so that it works as a band pass filter. So practically the inductor part passes some lower the lower frequencies than that. Okay, maybe I will just make a drawing so it makes more sense that way. There we go. So drawing, we have an inductor, then we have a capacitor, and then we have that loudspeaker like this. So thinking of the capacitor, it's a high pass filter, RC high pass filter like this for current, and for the inductor, actually it's a low pass filter. So if your low pass filter property is like that, then this is the middle band here that passes through. And okay, so this actually do exist in the world. Real life example that works. If you are into the building your own the audio equipment, there are plenty of nice websites that give you much better design parameters than this one to make your own loudspeaker. But this example is cheap, and you know how much these good loudspeakers are actually, how expensive they are. I would guess that Genelec does not use this kind of the crossover filters. That's my guess. Okay. Let's have a short break again, and then actually we continue a little while with the power.